All right, so page 488, section 7.1, solving systems of equations. All right, we have solved systems of equations in Algebra 1 and Algebra 2. So we're going to start with that same material. We will build on it and get into some more elaborate things when we get to the end of the chapter. But as we begin, very similar to those things that we've learned previously. There are lots of different ways to solve a system of equations. You can see that we're going to learn several different methods. We've got substitution and graphing today in 7.1, and then tomorrow we'll look at elimination in 7.2, and then Gaussian elimination in 7.3, and we'll even solve some systems with matrices in the next chapter, in chapter 8. What we mean by a system of equations is when you have more than one. So, for instance, let's say that we're looking at these two linear equations. This is a system of linear equations with two unknowns, x and y. But you can have systems that have three unknowns, x, y, and z. You can have systems that are nonlinear, like maybe they're made up of a parabola and a circle. And so that's why we need so many different methods for solving. Probably our favorite method is elimination that we'll be looking at tomorrow. But the only downside to that is you'll notice that it works with linear equations with two unknowns. So what do I do if I have something that's nonlinear or if I have three unknowns? I'm going to need a different method. And so that's why we learn several different methods. When we talk about the solution to a system, a solution to an equation, if I'm just looking at x plus y is equal to 4, the solution to that equation is any ordered pair that makes that equation true. So I might use like 2, 2 or 1, 3 or 3, 1. Any of those would be a solution to that equation. But if I want a solution to the system, then that means I have to find the ordered pair that makes both of those equations true. So even though 2, 2 might work up here, it does not work down here. It wouldn't be a solution to that system. So that's what we're looking for when we're talking about solving. So let's start with systems of two linear equations with two unknowns. All right? If I have two equations that are both linear, they're going to graph as lines, there are only a certain number of ways you can draw two lines, right? You could draw them so that they're parallel. You could draw them so that they intersect. Maybe they're perpendicular and intersect at a 90-degree angle. Maybe they're not, but they're intersecting. Or they're overlapping, and that just means one line laying on top of the other one. Those are the only three ways that we can draw two lines. The key for us is going to be right here. Solution equals intersection. Here's the thought behind that. Let's say that we're looking at these intersecting lines right here. Every single point on this first line, every single point is a solution for that line. If we're back down here talking about x plus y is equal to 4, we might be sitting here plotting 1, 3, 2, 2, 3, 1, and then drawing a line to connect those dots. So if it is on that line, it is a solution for that equation. So then if I were to go back and graph x minus y is equal to 2, every single point on this line would be a solution for that equation. So if I'm looking for the one solution that works in both equations, it's got to be this one little point right here because that's the only one that is on both of those lines. So my solution to the system would be the intersection of the two lines. And so again, that's our key, solution equals intersection. So for parallel lines, because they never intersect, then they have no solution. The intersecting lines intersected in one spot, so they would have one solution. And overlapping lines have infinitely many intersections. Like you can see there's an intersection here and here and here and here and here and here and here, and it's going to keep going to infinity. So they have infinitely many intersections. That means they have infinitely many solutions. Now, infinitely many solutions and all real numbers are not the same thing. And students sometimes get that confused on the test. The reason why you can't say all real numbers instead of infinitely many solutions is, yes, there are an infinite number of points on this line that are going to work in both of those equations, but that doesn't mean that a point over here off of those lines is going to work. And so if I say all real numbers, I'm saying everything on the face of the earth is going to work. This point over here is not going to work. So it would have to be a point on those lines. So yes, there are an infinite number of them, but the difference there being infinitely many solutions, not the same thing as all real numbers. Okay, so let's look at example 1. Example 1, we have two linear equations, and we said today that we wanted to solve by both substitution and graphing. So let's take example number 1, a system of two linear equations with two unknowns, and let's solve it by substitution and by graphing. All right, let's start with substitution. You might remember that with substitution, you're going to solve one of your equations for one of your unknowns. It does not matter which one. In a subsequent example that we're going to look at, I'll point out to you that a lot of times you can work smarter and not harder by the way that you choose the variable that you solve for. But in this case, it pretty much, doesn't matter if I choose the first equation or the second because they're equal in difficulty. And it doesn't really matter if I choose x or y. So I chose the first equation and I solved for y. But you could have chosen the second equation and solved for y, or you could have chosen either of them and solved for x. The reason this is called substitution is I'm going to take what I just got for y, 4 minus x, and I'm going to substitute it in the place of y in the other equation. Why do I have to do that? I can't solve for x and y at the same time. But if I replace y with what it's equal to, 4 minus x, now everything's in terms of x. Now that I can solve. So we can go through and distribute that negative. So we'll have negative 4 and a positive x. Combine our two x's, add our 4 to the other side, and then divide by 2. So we'll get x is equal to 3. All right, once you know x, how do you find y?
You just plug x back into the originals.
Yeah, I'm going to plug x back into my equation. Now, which one? I can put it back into the original first equation, the original second equation, or the altered first equation over here. That altered first equation would probably be easiest because I've already solved it for y. And so I could just put 3 in the place of x, and I've got y is equal to 1. So there's my solution, 3, 1, my ordered pair. Now, on the homework on a lot of these, they're going to tell you solve it algebraically and check it by graphing, or solve it by graphing and check it algebraically. So we want to be able to do it both ways. So let's take this exact same system, and this time let's solve it by graphing. All right? You can graph these however you want to. I'm going to make an XY chart. So I took the first equation, x plus y equals 4. I'm going to put 0 in for x. So if my x is gone, then y is 4. And then I put 0 in for y. So if my y is gone, it's like you can put your finger over top of that, and you'll get x is equal to 4. So I plotted 0, 4, and 4, 0, and drew my line. If you'd rather use slope-intercept, whatever you want to do. All right, second equation, same idea. I'm going to go through, and again, I used an XY chart with the x and the y-intercept. All right, and what did we say the solution would look like on a graph? How do we identify it? It's the intersection, right. And you're exactly right. That point of intersection does look to be 3, 1. So the solution that we got over here algebraically is the intersection that we got over here graphically. So again, on the homework, they'll typically have you do it both ways so that you can see they're the same. Now, what's the only downside to graphing?
Inaccuracy.
Inaccuracy, yeah. If you look at my graph, I mean, I tried diligently to make these little tick marks all the same width, and I used a straight edge to draw my line to try and be really precise, but honestly, I mean, 3, 1 is actually a little bit more over here. So my graph is off a little bit. So that's the biggest problem with graphing is it's just inaccuracy. You know, what if my answer is really supposed to be 2 and 7/8 1 instead of 3, 1? If my answer is really supposed to be 2 and 7/8 1, I'm not going to find that on my graph. Because how am I going to differentiate between 2 and 7/8 and 2 and 5/16? I mean, that's such a minuscule little amount. It's going to be hard for me to see that on a graph. So it's also pretty time consuming by the time that I go through making 2XY charts and plotting points and that type of thing. So what could alleviate that? Graphing calculator. All right, so grab your graphing calculator if you would. The graphing calculator can help us with our inaccuracy and also with the length of time that it takes us to do this. All right, if I'm going to put this system of equations in my graphing calculator, what do I have to do first?
Y1.
Solve them for y, right? So let's go through. If I have x plus y is equal to 4, then I'm going to need to solve that for y. So I'm going to subtract the x to the other side. So in y1, I'm going to put in 4 minus x. And then my second equation was x minus y equals 2. So if I solve that for y, I'm going to add the y to both sides and subtract the 2. I'll get y equals x minus 2. So I'm going to put that in y2. So I'm going to go to y equals, and in our first one we can type in the 4 minus x, and then scroll down to y2 and type in x minus 2. All right, I'm going to start with graphing this on a zoom standard. That's the one that's tens all the way around. So I'm going to choose zoom number 6. And that gives us a pretty good picture. It might be easier if I were zoomed in a little bit. So remember, the other one we like to use a good deal is zoom decimal, zoom number 4, because that's the one that literally counts by tenths, and we get nicer, cleaner, neater numbers on that one. And then it's really easy to see that point of intersection right there at 3, 1. Also, if it really was something like 2 7/8 1, I am going to be able to get that accuracy with my calculator because it'll give me like 9 decimal place, 8 9 decimal place accuracy. So we've done that before. How do I find that point of intersection? Yeah, the intersect button, which is in second calc. So I'm going to go to second trace, which is my calculate menu. I'm going to choose option number 5, which is intersect. And when I do, it's going to ask me, do you want me to use this for your first curve? And you can see it's already positioned itself on this first curve, and it's telling me I'm using what you've got in Y1. So I'll tell it enter for yes. And then it jumps down to what I've got in Y2 and says, you want me to use this for your second curve? So I'll tell it enter for yes. And then they want to guess. A lot of us get in the habit of just hitting enter right here where we are. And, you know, that's perfectly fine. Their intention is for you to come up here close to that point of intersection before you hit guess. The only drawback about just hitting guess wherever you are, we are going to get to some of these today where they have more than one point of intersection. If they have 2 points of intersection, whichever point you're closer to when you hit guess is the answer that it's going to give you. So I'll have students that keep doing the same thing over and over and over again, and it keeps just giving them that one point and they can't figure out why. So you have to go position your guess close to the point that you want it to find, and then it will give you as many points of intersection as there are. So guess closest to the one that you want it to find. And so sure enough, it verifies for me that that point of intersection is 3, 1. So just for review of what we just did, we put both of our equations in y equals, and then we graphed, and we went to second trace, which was our calculate menu, chose number 5, intersect, and it said, do you want me to use what's in y1 for the first curve? We told it enter. Do you want me to use what's in y2 for the second curve? And we told it enter. And then it asked me for a guess. We got as close as we could and hit enter. And then it did give me that point of intersection at 3, 1. So that would take care of the time and the inaccuracy problem. All right, look at example number 2. For example number 2, they give me a word problem. And so I just want to go through this one with you and set it up. We don't need to work it out, but I want you to see how you could take a word problem and create a system from it as well. So example 2 says a total of $12,000 is invested in 2 funds paying 9% and 11% simple interest. The yearly interest is $1,180. How much is invested at each rate? We've said with word problems the last sentence is pivotal because that's usually what you're trying to find. And they said how much is invested at each rate. So that's my unknown. I don't know how much is being invested at the 9% rate. I'll call that X. And I don't know how much is being invested at the 11% rate. I'll call that Y. Since I have two unknowns, I'm going to need two equations. I need a system of two equations to solve those two unknowns. So let's go back to the information and see what they tell me. It says the total of $12,000 is invested in the two funds. Okay? So if I take the amount in the first fund and put it with the amount in the second fund, total is $12,000. So what does that imply? Addition, subtraction, multiplication, division? Addition, right. So what was the amount that I had in the first fund? You're like 8 steps ahead, and that's awesome. What's the amount invested in the first fund? What did we call it? X, right. And the amount invested in the second fund was Y. So you told me to add those together. So if I add X and Y, what am I going to get? 12,000. So that's going to be my first equation. All right, then the second thing that they tell me is that the yearly interest is $1,180. Now, remember that interest is equal to principal times rate times time. Principal is the amount you have invested. So let's start with the first one up here. For the first one up here, the amount that I had invested was X, so that'll be my principal. My rate was 9%, but anytime that you're going to multiply by a percent, what do you do? Yeah, 0.09, change it to a decimal, exactly. And then our time was 1 year. So we can go through and say X times 0.09 times 1, and the interest on that first account is just going to be 0.09X. All right, so let's do the same thing with that second account. For that second account down here, if I do interest equals principal times rate times time, what's the principal? Y. What's the rate? 0.11, and what's the time? Right, so I could go through and multiply those, and I'd have 0.11y. Okay, so this is the interest I get on the first account. This is the interest I get on the second account, and it says the yearly interest is $1,180. So what do I need to do with those two? Add, subtract, multiply, divide. Yeah, I'm going to add them up, and when I add them, it has to be equal to the yearly interest, which is $1,180. Okay? Now, something we had talked about last week is if you don't want to have to work with fractions, you can clear them out by multiplying by the least common denominator. Same idea here. If you don't want to have to work with decimals, you can multiply by the power of 10 that has the same number of zeros as the number of decimal places you want to get rid of. Here's what I mean. I want to get rid of 2 decimal places, so I'm going to multiply by the power of 10 that has 2 zeros. That would be 100. If you want to get rid of 3 decimal places, you're going to multiply by the power of 10 that has 3 zeros. That's 1,000. If you want to get rid of 1 decimal place, you're going to multiply by 10. Yes. So we could finish solving it from there. I just wanted you to see how to set that up. Okay, so then we get to example number 3. And in example number 3, this is not a linear system, right? Because this is y equals x squared. That's a quadratic. What's a quadratic going to graph as? Parabola. So if I think about the possibilities for a line in a parabola, I might get 1 intersection or no intersection like we saw before, but I might also get 2 intersections. They'll bring back anything that we've already learned this year. We've learned both circles and parabolas, so they could give me something like this where I get 4 intersections. So if you get more than 1 intersection, don't think that you've done something wrong. All right, remember we said for substitution, you can solve either equation for either unknown. Here's where we need to work smarter, not harder. Which equation do you want to work with, the first one or the second one? The second one. And do you want to solve for x or y? How come I want to solve for y? Because 2 reasons. If I solve for x, I'm going to get a fraction. Not a fan of that. And if I solve for x, I got to plug it in here and here. If I solve for y, I only have to plug it in here, right? So absolutely, I want to take that second equation and solve it for y. And as we said earlier, the whole idea of substitution is to take what we get for y and then substitute it into the other equation in place of y. So let's take what we just got, 2x plus 1, put it in the place of y in that other equation. Watch out that you distribute that negative, so we'd have negative 2x minus 1. Combine like terms. And they were kind enough to give us one that we could factor. Heaven forbid, what if this did not factor? Remember that thing called the quadratic formula? And remember that you do not have your graphing calculator for this test, so you do need to be able to do quadratic formula by hand other than using the program on your calculator. What if when you were solving here you got imaginary answers? If you get imaginary x's, how are you supposed to plug that in and find y's? Yeah, that just means that you don't have a solution. Exactly. All right, so we are going to take, as we did earlier today, our x's and plug them back in. And because we got 2 x's, we're going to get 2 y's. So we're going to get 2 solutions. So we're probably looking at a scenario kind of like this if we graphed it to check it. So we've spent a lot of time today talking about what one solution looks like or what intersecting looks like. So let's review for just a second what no solution or infinitely many solutions might look like. We just said no solution comes when you solve a quadratic and you get imaginaries. But another way that you get no solution is if when you're solving, if all your variables drop out and you're left with an untrue statement like 0 equals 6, that means there's no solution. If you're solving and all of your variables drop out and you're left with a true statement like 4 equals 4 or 0 equals 0 or x equals x or some type of an identity, that means that you have infinitely many solutions. Okay, so that's what that would look like. All right, and here is your homework for tonight.